Hey friends, this is all about gravity today. So, universal law of gravitation, according to Newton. So he had three laws, the first, second, and third, but he also had this universal law of gravitation, which kind of explained how everything moved with his three laws. And that's when people started buying into this idea that maybe the Earth is not the center. I guess it makes more sense that the sun is the center of everything. So mainly today talking about gravity and how that affects things, orbits and so on. So here we go. Alrighty guys, pop quiz. I know you wanted a pop quiz. So astronauts in circular orbit about the Earth, which vector describes the velocity? The A, B, or the C? The answer is, it is the B. Whoops. I thought it would show you the answer. My bad. The answer was the B is the velocity vector. It's trying to go in a straight line. There is something keeping it from going in a straight line. So which vector might describe the acceleration? That's the C. And why is it the C? Which vector might describe the gravitational force acting on the astronaut? It's the letter C. So this is an unbalanced force that causes this astronaut's velocity to continuously change direction, not speed, because it's perpendicular. A perpendicular force cannot change the speed of things. It can change the direction, but there's no component of the C that goes in this direction to make it go faster, and no component backwards to this letter B over here to make it go the other, to slow down. So since it's perfectly perpendicular, this force can't speed it up or slow down this astronaut. The astronaut just remains in orbit, free falling the whole time. Because this person is actually falling around the Earth. But it happens that they're going fast enough in this B direction that the force will always stay perpendicular with this astronaut, only changing the direction. And it has to be at a particular speed at that distance. And that's what we'll eventually get to that portion. Okay, not quite yet. So the answer is C, and that's why the acceleration is in the C direction. It's an unbalanced force that causes the change in motion towards the C, which is centripetal acceleration, but the velocity is changing. There's no A here, guys. There's no outward force on the astronaut. There's nothing contacting the astronaut to shove him this way. There's no field force throwing the astronaut this way in anti-gravity, only gravity pulling this way, changing the astronaut's motion. So they feel like they're falling because that's exactly what they're doing. Nothing is pushing on the astronaut. They're just falling around the Earth. Alrighty, so which one of these experiences weightlessness? Bob, stationary, located billions of light years away from a star or planet. Ted, falling freely in a broken elevator. Carol, orbiting the Earth in a low orbit. Alice, or Alice, if you're French, Francais, who is far, so Alice is far from any significant stellar object, rapidly rotating space station. Woo! Which one is it? It's not Alice, because something's shoving on her. Unless she's hanging out in the middle of this rotation, then nothing's shoving on her, and she could be in a free fall. But since they're more than likely they're saying she's on the outside or somewhere spinning, there will be something pushing on her to change her motion all the time. It won't be Alice. So the answer is all of them except for Alice, which is C. Yep, Bob, Ted, and Carol. All feel like they're weightless. We're going to find out there's no way to escape gravity. There's no place it ends. But if you're falling, everything accelerates at the same rate. It seems like you're weightless. Okay? Or there's nothing pulling on you. All right, let's talk about this gravitation thing from a few hundred years ago that Newton derived from things orbiting other things. Turns out mass matters, guys. Mass matters. The bigger any one of these two masses would be, the larger the force. If I double this mass, the orange mass over there, that would double the force. If I double the blue one, that would double it. And a double-double is a quadruple, right? So mass matters, but it's directly proportional. Double the mass, double the force. R is the distance from center to center. So it varies with the square. This is called the inverse square law. More about this later on. So what that means is the bigger this distance, the smaller the force, because it's inversely related. But it's not just double the radius, half the force, it's 1/4. Because if you were just to double that radius right over there, okay, let me go ahead and do some drawing for you. I know how much you guys love the drawing. So if I were just to double the radius down here, remember the radius is on the inside of the parentheses, a double is really 1/4 the amount of force. If I were to triple the distance between them, 3 squared is 9, that would be 1/9 the force. Okay? Or if I did something else crazy, I don't know if I can even erase on here, so I'll just scribble on here. What if instead I halved the radius, huh? So if I halve the radius, and let's go with the blue on this one. So if I just go with a half the radius, and now they're getting closer, where a square of a half is a 1/4. So if we have a 1/1/2 squared, right here, 1/2 squared, so that'd be 1/1/4. Well, that actually is 4 times the amount of force. If you get to be 1/3 the radius, 1/3 squared is 1/9, 1/1/9 is 9 times the force, and so on. So that's the tricky thing people forget about. It's not a directly proportional to the inverse. It's to the inverse of the square there. This G thing is something you can't change. It's a constant. Newton didn't know exactly what that was. We'll see a video here in a moment that explains how you would find the G thing right there. So this is a constant because a mass times a mass divided by a distance squared is not in newtons. So this number straightens it out. It's a constant. And it's universal gravitational constant. That means it's the same at least in our universe. Okay? So this number doesn't change. It's 6.67 times 10 to the negative 11th units. Alrighty? Let's keep on rolling here. So the law of universal gravitation states that every object in the universe attracts everything else. Okay, so the point is, guys, every mass, as long as it has a mass, an inertial mass, there's an attraction. According to this formula, this universal law of gravitation, there's an attraction. And sure, it gets smaller the further you get away, but it gets infinitely close to zero, this force, so technically it doesn't ever end. Okay? So, the greater the mass is, the greater the force of attraction. Aww. The greater the distance, the smaller the force. With the square, though. Twice as far away is 1/4 the amount. 3 times further away is 1/3 the amount, and so on and so forth. Alright, so there's dude Cavendish. This is maybe a little over 100 years later than this Newton person when he did all those experiments and describing the physics behind everything. He had this, came up with a way to test and measure that big G thing. So to measure that big G thing, let's back it up a little bit. That means you have to know the force, somehow have to measure this force between things and the distance center to the center. Well, guys, we're going to find it because this is negative 11. If we try to find the force between you and your buddy there is a gravitational force between you and your buddy there, but it's so small it's not really measurable. So that is the trick. How do you go back over a couple hundred years ago and measure that force? Because you might measure the masses and the distances pretty easy. How do you measure what that force is? Because this is a really puny force between these things. Well, here we go, guys. Here's the video of how would you know, how do you find the G thing?
Introduce you to chemist Henry Cavendish. How's it going, Henry?
Fine, thanks.
Henry is known for the Cavendish experiment. He was the first person to measure the force of gravity between masses in a laboratory and to produce an accurate value for the Earth's density.
Correct.
His work led to accurate values for the gravitational constant G. What's up, G?
Yo.
And the Earth's mass. The measurement of the gravitational constant allowed the mass of the Earth to be calculated for the first time. This also allowed the calculation of the masses of the Sun, the Moon, and the other planets. The first time this constant was used was in 1873, almost 100 years after the Cavendish experiment. Variations of Cavendish's results are still used today.
Indeed.
Now, for this experiment, he used a device with a torsion balance. like that, to measure the gravitational attraction between two 350-pound lead spheres and a pair of 2-inch, 1.61-pound lead spheres. Using this experiment, Cavendish found that the Earth's average density is 5.48 times greater than that of water. It turns out that any two masses have a gravitational attraction for one another. If you put two bowling balls near each other, they will attract one another gravitationally. The attraction is extremely slight, but you could measure the attraction if you had the right equipment. From that measurement, you could determine the mass of the two bowling balls. The measurement of our planet's weight is derived from the gravitational attraction that the Earth has for objects near it. Cavendish performed his experiment in an outbuilding in the garden of his estate. For years afterward, his neighbors would point out the building and tell their children that this is where the world was weighed.
There you go, guys. That's where the Earth was weighed. Okay. All right.
For just $67,
All right.
you can make as many videos as you want.
All right, so that's a little bit about Cavendish. So it's kind of a delicate experiment. You didn't have a laser back then, but it turns out you shine a light on a mirror, any very slight fluctuation in that mirror whatsoever, even though you can't even hardly tell it's moving back and forth, makes a pretty big change in angle across if you have a wall way back over here. So by knowing how much force it takes, so the tensile strength of the string to twist, by the amount of twist on the string on this mirror, by the angle it moves through, you can go back and solve for what that force is. And if you know the masses and the distance between the two, you go back and solve for the G. So back then is a pretty big deal to go back and measure that G. And then once you know the G, you can easily find the forces between things. Alrighty. So here's the story. So a mass and a mass attract each other with an F, a force the size of F. What if one of these gets twice as massive? What happens to the F? Larger, smaller, and if it's larger or smaller, by how much? Twice the amount, because twice the mass is twice the force. What if now we double this other one? It's a double-double, and what's a double-double? A quadruple, 4 times the amount of force. What if this is an F, but one of these is a 3M, and one of these is an M? What's the force like? 3F. So that's the easy one. That's the easy math, because the mass is directly proportional to the gravitational force. You double one, the other doubles. You triple one, the other one triples. So that's the easy math. The tricky math is the distance, okay? So remember, m times m divided by r squared, or in this case, d squared times the g, is an F. So what if you double the distance? More or less? Less, but how much? So if it's twice the distance, it is 1/4 the force, right? It's that inverse square law thing. What if you get twice as close? So 1 over 1 over 1/2, but you got to square the 1/2. 1 over 1/4 is 4 times the amount of force, because you're twice as close. What if you're 3 times closer? That'd be 9 times the force, right? All right, here's the big kahuna, guys. A double-double, that's a 4 times the force, right? But it's twice the distance. So if you have a double-double, which is 4 times the amount of force, but twice the distance is 1/4 the force, 1/4 times 4 is F. So even though we did a double-double, which is 4 times the force, because it's divided by twice the distance, which is square the twice in the bottom, it becomes a 4. 4 divided by 4 is just 1F, the same force. Alrighty. So, couple sample problems here, but we're going to stop here so I can YouTube this. Alrighty, and we'll continue on in a second.